We all think we know what gravity is, right? But what if what we know isn't the whole truth? What if gravity, as we understand it, is just a trick our minds play on us? Today, we're going to question everything that you thought was real. But before discovering the hidden secrets that rest at the heart of gravity, let's first subscribe, like this video, and hit the notification bell to stay updated on our latest content. Sir Isaac Newton pioneered our recent comprehension of gravity as an attractive force in the 17th century. The renowned apple incident, where Newton observed an apple falling straight down, led him to ponder the existence of a certain force causing this phenomenon, ultimately formulating the universal law of gravitation. This law explains that an apple accelerates as it falls due to the force of attraction between it and the Earth, determined by their respective masses and inversely proportional to the square of the distance between them. In simpler terms, all entities possessing mass and energy attract each other and exist in a free fall relative to larger bodies. The popular formula represents the underlying principle. Gravitational force equals the multiplication of the primary and secondary mass divided by the square of the orbital radius. Newton also introduced the gravitational field surrounding all material entities, a mental model that continues elucidating gravitational interactions. As per Newton's third law of motion, the Earth is likely drawn towards the apple. However, this movement is imperceptible due to its negligible magnitude and the principle of force equals mass as described in Newton's second law. Moreover, Newton postulated that gravity influences celestial bodies, including the Moon, despite their considerable distances. Through an imaginative experiment involving a cannon fired from a mountain, he demonstrated that an object propelled with sufficient force could perpetually fall without ever hitting the surface, resembling the state of celestial bodies as they orbit. This insight solidified Newton's belief in gravity as a universal force operating uniformly across the universe. Newton's laws complemented the theories of Johannes Kepler, a fellow scientist who described the movement of planets. According to Kepler, every planet moves around a star in a path shaped like an egg, called an ellipse, and the distance between the planet and the star is always changing. The force that keeps the planets moving this way is the same one that pulls apples to the ground on Earth: gravity. Sometimes the planet gets close to the star, called perihelion, and sometimes it moves far away, aphelion. But it always covers the same distance at the same time. Newton's laws tell us more about how gravity affects the speed of big objects and how increasing the distance of the orbit affects how long it takes for one complete rotation. But Newton's laws don't explain everything. Take Mercury, for example. Its orbit around the Sun is a bit off, and its closest approach to the Sun keeps shifting in a slow circle. This is called precession. Mercury's precession happens faster than we'd expect from Newton's laws, by about 43 seconds every 100 years. Newton could not explain this mystery. Almost 300 years later, Albert Einstein developed a new understanding of gravity. In his general theory of relativity, Einstein explained that heavy objects could bend time itself, and that bending is what we experience as gravity. This was quite different from Newton's idea. Einstein used the example of a person in a falling elevator. As the person falls, he doesn't feel his weight because he and the elevator are falling at the same speed. But when the elevator goes up, he feels heavier. If the elevator had no windows, he couldn't tell whether he was falling down or moving up. According to Einstein, we always fall until we hit something that stops us. This idea led to a new understanding that gravity isn't a force. Let's break down Einstein's theory of relativity and gravity in a simpler way. According to Einstein, gravity isn't a force pulling things together, but more like a bend or a warp in time and space caused by heavy things like planets and stars. If we try to imagine this warp, it's like those heavy objects are sinking into a 3D grid, warping or bending the lines around them. This bending makes other things in space move towards the heavy objects, making it seem like they're being attracted. If you were aboard the International Space Station, the ISS, flying close to Earth, you'd be moving in a circle because of this warp, even though it would seem like you're going straight. This is also why, on Earth, if two people move towards the North Pole from a distance, they'd meet each other due to the Earth's curve. Even though light doesn't have mass, it still follows this warped grid. This means that light can also bend its course when passing by heavy objects. Astronomers Eddington and Davidson confirmed this when they observed a solar eclipse in 1919. They noticed that light from stars was bending more than what Newton's gravity had predicted. Einstein's theory also helps explain why Mercury's orbit around the Sun is a bit off. According to Einstein, the curve in space caused by the Sun shifts Mercury's orbit by about 43 seconds. Lastly, Einstein's theory predicts that light can stretch and lose intensity when it passes by massive bodies. This means that light can change color, a phenomenon called the redshift of light, which Newton's gravity doesn't predict. In 2016, scientists saw this happen when they observed a blue star, SO2, passing close to the black hole Sagittarius A. The star's light changed to red, again confirming Einstein's theory. Einstein's model of gravity has dramatically improved our understanding of the universe. Although not all tests have confirmed its reliability, it has provided many insights into time and space. Still, Newton's model can compete with Einstein's general relativity, that's GR. For instance, in the 1930s, Danish astronomer Jan Oort observed that stars at the edge of disk galaxies rotate at constant speeds, contrary to expectations. This led to the concept of dark matter, first proposed by the astronomer Fritz Zwicky. Current estimates suggest the universe comprises roughly 70% dark energy, 27% dark matter, and just 5% ordinary matter. However, the existence of dark matter hasn't been definitively proven. Astrophysicist Mordechai Milgram proposed a modification to Newton's gravitational model, called Modified Newton Dynamics, or MOND, to explain this galactic rotation. He added a constant AO, which defines a critical acceleration point. Below this point, Newton's laws are replaced by GR, equalizing acceleration irrespective of distance from the center. This theory explains the motion of stars in many galaxies without invoking dark matter. However, MOND has issues. For one, it can't completely rule out dark matter, as galaxy clusters and the MOND analysis still indicate a mass deficit, implying the presence of dark matter. Lastly, a significant issue with Einstein's gravity is its inconsistency with quantum mechanics. GR operates on causality, while quantum physics is probabilistic. This means GR can't be applied at quantum levels, and quantum mechanics can't work with macroscopic objects. A new theory of quantum gravity, which can explain the interaction of objects and fundamental particles, is needed to resolve this. Despite certain incongruities, the repeatedly validated model of Einstein's theory of gravity continues to underpin contemporary research, testifying to its enduring relevance. While it is uncertain if general relativity will encounter a similar fate as Newton's law of gravity, it cannot be underestimated how instrumental the alignment of this model with other realms of physics is for the scientific community as a whole. Until a new theory of gravity emerges, we can confidently assert that gravity is not merely a force. If you found this topic intriguing, give us a like and share our YouTube channel and this video with your friends and fellow science enthusiasts. Your support assists us in continuing to bring such insightful content your way.